Hello everyone and welcome back. In the last video, we already saw that how we can do fault detection using classical statistical method such as just thresholding, assuming that our data belongs to normal distribution. We saw it got pretty good results. In the end, we also did F1 score analysis, and using the F1 score analysis, we can clearly see that most of the faults are easily detectable by this kind of method. So probably if your goal is if your standard of your industry is satisfied by this kind of performance, then maybe it is not recommended to go for machine learning. Rather stick to the statistical method because this also gives you an additional interpretability. You know exactly which sensor is deviating its threshold, so you can pinpoint that where the fault has occurred according to the given sensor. So yeah, but there is one thing I wanted to say is I basically want to benchmark all the methods that we are going to use in this video series, all the unsupervised method. So what I'm going to do, I'm going to create a single F1 score matrix for each method. So this is the first method. So for that, what I'm going to do, I'm just going to average them all. This is basically all the F1 score values we got in the previous video, and using that, I'm just going to average that out. One additional thing I did is along with F1 score, I also obtained the accuracy score just to have a rough idea. F1 score is more conservative, as in if your fault is very costly, then you should always look at F1 score rather than accuracy score. Okay, we often see that the F1 score is lesser. The F1 score is lesser than the accuracy score in all the case because it combines recall and precision. So what I did, I basically created a for loop to average out the F1 score and accuracy score. This code is just same as the previous one. Just instead of printing them out, I'm just going to put them in a list, F1 all and accuracy all, and I'm just going to obtain the mean of those two value for benchmarking. So I got this two value for F1 score, I got 0.673, and for accuracy score I got. And now I'm going to keep track of them. And if you want to also follow along, then you can go to my GitHub, and in my GitHub, go to repositories and the first one. And here you can see I'm benchmarking all the different kind of method I'm planning to do. So the first one is statistical method, and we see that the F1 score obtained is 0.67, accuracy score is 0.78. And in this video, we are going to do PCA based reconstruction. I'm going to explain more what is this. And using this, I got a F1 score of 0.53, but a higher accuracy score. We'll see, dive into that. And there are other methods that I'm going to uh, show in this video series, and also I'm going to populate this F1 score and accuracy matrix as we go along. Okay, so now let's come to PPT so that I can demonstrate what is the goal of today's video. We are going to use PCA based reconstruction for anomaly detection. The idea for this I got from a research paper, and I'll give the link to that research paper in the comment section so that you can check it out. And they have also used the Tennessee Eastman process for their benchmarking. So what is PCA analysis, which stands for Principal Component Analysis? What we do is this is a iris dataset where we have petal length and sepal length, the distribution for Setosa, Versicolor, and Virginica. But if we do the principal component analysis, we can see that using the first principal component, we capture the highest variance, and the second highest variance is captured by principal component 2. This is usually used as a dimensionality reduction in machine learning, many of the machine learning case. So intuition of principal component analysis. So for now, our data set is n cross 52, where n is the number of sample and 52 is the number of sensor read. And when we fit a PCA model along with that, we get the, let's say W is the weight matrix or the transformation matrix for PCA, principal component analysis. And for when we fit a principal component model, um, we need to provide how many principal components we want. So this principal component can be anything between 1 to 52. So if we take principal component equal to 52, it will capture the all the variance there is in the data. But if we take like for one or two principal components, it will take it will capture different amount of variance. So what we do then is just multiply this learned matrix which you get by fitting the data on a principal component. We just multiply this two. This is n cross 52 and the weight matrix is 52 cross principal component. So our n, the x PCA, the PCA transform is n cross PC, which is the principal component. So let's say if we take principal component equal to 2, then our 52 dimensional data is converted into 2 dimension. Though it does not capture all the variance, but it is easier to plot. Alright. So often principal component is not equal to 52, and that depends. The lesser the principal component you take, the lesser variance it will capture. And next what we can do, we can take inverse PCA. This is the principal component value we got. We can use this in inverse PCA function to reconstruct back the original dataset. We don't have to know the maths behind it. We'll just use it based on scikit-learn. But if you want to know more, it's given in the paper that I'll provide. So X inverse PCA will be n cross 52. But the problem is, as the principal component we are taking is less than number of variables, this reconstruction will not be equal to the actual variable that we took in the first place. So the inverse transform value, the matrix we'll get will not be equal to our starting matrix. This is because we are not capturing all the variance. And what is reconstruction loss? We saw that the reconstructed matrix is not equal to the original one, and we can just define a reconstruction loss based on the mean squared error between these two matrices. And what we hope is, hopefully the anomaly data that we did not use for the training of this principal component analysis will give us higher reconstruction error compared to the normal data. And then we can just detect the anomaly by thresholding, by putting a threshold for reconstruction loss. And now we're going to see the same thing in the Jupyter notebook. All right. So now let's see the code here. So first of all, we'll import the necessary libraries. Next, we'll import the dataset, which is very similar to the methods that we did before. Then we concatenate the faulty and fault-free data into a single data frame so that it will be easier to access. Next step, this is important when you do principal component analysis because the scale between different sensor data is different. So see, the XMEA ranges from 0.2 to 0.3, but whereas this one XMEA3 has 4,000, it ranges from 4,000. So there is a huge scale gap between different feature. So it is good to first standardize them to have a mean of 1 and standard deviation of mean of 0 and standard deviation of 1. So after you scale that, you can see that yeah. So now we can see that all the data ranges between -1 to 1. So which is a good thing to before you do any kind of principal component analysis. So then we'll just fit a principal component model. We'll import from scikit-learn, initialize it, and just fit transform on the scaled data. And this scaled data is, mind you, this is just the fault-free data. All right, because I have mentioned here fault number equal to 0. That means I'm only using my fault-free data to to get the mean and standard deviation so that I can uh, transform other data as well. And also I'm fitting using the fault-free data itself. After that, I did this. I basically copied it from Stack Overflow that someone did a nice plotting for a principal component analysis. Is one important thing in PCA is what is your explained variance. Like suppose first of all we need to define the number of components we want in our PCA. If you do not define, it takes the number of features to be a principal component. That means it takes all the features, and that means you will get the explained variance. is 100%. But I'm just using this to plot this. So what is this plot? Let's see. So this plot shows that uh, with increase in number of principal component, how much variance is captured. So definitely one, if you take all the variable, we have 52 variable. If you take all the 52 variable, then the variance captured is 100%. Explained variance is 100%. But we don't need to keep all. Maybe we can say that okay, 90% variance of my data is good enough for me. So for that, you need to take around 40 features, 40 principal components into your consideration. So yeah, that was about it. Maybe for different data set, this totally varies. For some, only the first five components explain 90%. So it depends upon the data set completely. It is an iterative process. You need to look for each different case. So first, what are we going to do? We are going to fit a principal component model according to the variance we need. So for that, I'm again going to call the standard scalar method, and I'm going to transform the fault-free data. So when I say fault number equal to 0, that's the fault-free data. Like X fault-free is the scaled fault-free data, just standardized already. And then using decomposition from a scalar, I'm going to again initialize another principal component model where I'm keeping n components equal to 0.9. So here this 0.9 means how much variance you would like to have in your principal component transformation. So when you put 0.9, it captures 90% of the variance in the data. All right, and then using this PCA anomaly, I'm going to train this PCA anomaly using my fault-free data. All right. So now what will I do? I'll just do a cumulative sum of all the explained variance ratio. I say that 90% of the data is captured, which I already defined here. Okay. So what now I got is I got the fitted model of PCA, and now I can obtain the reconstruction loss that we saw. So I'll create a new function called reconstruction loss, where the input will be my trained PCA model and the data I want to obtain reconstruction loss for. So PCA is the already fitted model of fault-free data. And the first case, what will I do? Whatever my input will be, I'll do a transform, PCA.transform. I'll store that in XPCA. Then using this XPCA, I will do PCA.inverse transform to obtain the reconstructed value of the original dataset. So this X recon and X have the same dimension. To obtain the reconstruction loss, I'll just take the mean squared error between X and reconstructed value, X recon. And that's it. That's my reconstruction loss. And hopefully this reconstruction loss will be higher for the anomaly dataset. So first of all, let's see how the reconstruction loss looks for the fault-free dataset. For that, what will I do? I'll call my function recon loss. The in PCA I'll put PCA anomaly, which is my already fitted PCA model. X fault-free is the scaled, is standardized data for fault-free scenario, and I'll get fault-free reconstruction loss. And then I'll just put a histogram using this fault-free reconstruction loss, and I see that this. So this ranges from 0 to 0.25, let's say, and it's little skewed, but you can say, okay, this is a normal, this belongs to a normal distribution approximately. And then now comes the important part where we'll do the reconstruction loss for the faulty data. And now I'm going to do the same. I'm going to range fnum from 1 to 21, where 1 is the fault number 1 to up to 20th fault. So first I will get the data frame for that corresponding fault. Basically all the data set. I'm not looking at different simulation run. I'm taking all the simulation run for that particular fault data set, and I'm taking df sample greater than 20.0. What does that mean is because the fault was introduced after 20th sample, that's why I'm taking those sample to be my 10th faulty. Then I'm scaling the data. So the SC is the already SC contains basically the standardized value of the fault-free case. I'm using that to transform this data. So X faulty is the transformed faulty data or standardized faulty data. Then obtain the reconstruction loss from trained principal component. Then I'm calling my reconstruction loss function where my input is PCA anomaly that we already trained on fault-free data and the standardized faulty data. Using this, I'll get faulty reconstruction loss. And then I'm plotting both the fault-free reconstruction loss and faulty reconstruction loss for all the different type of faults. All right, so let's see. So for fault number one, we can see that the fault-free has a different distribution than the faulty case. And yeah, there is some overlapping, but yeah, we can just say, okay, this is good. For fault 2 also, we can see there is a little bit of overlapping, which is not a bad case. Fault 4, fault 5, fault 6, 7, 8, 10. Yeah, you can see basically for different fault here, I don't even know where the fault free case is. I think it's very small because you can see this is about 200,000 and this one belongs to just 10,000. So it's very small. Same here also. It's pretty small. That's why we can't see it with naked eye. And then yeah, fault 14, 15. Basically, we can see that there is pretty good distinction between different faults. So now that we have seen all evaluated all the distribution for fault-free case and faulty case, what I'm going to do, this is my fault-free scenario. So I'm going to take the threshold based on this. So I'm going to obtain the mean of this distribution and the standard deviation. So mu plus 3 standard deviation will be my threshold. Similar thing that we did in the last class. So what I did, I obtained the mean of the fault-free reconstruction loss, the standard deviation, and mean plus 3 standard deviation will be my threshold. For this case, I obtained the threshold of 0.216, which you can see here is the normal data is lying between 0.2 most of the cases. So yeah, that can be my threshold. And using this threshold, so using this threshold, I'm again going to plot for a simulation run for different type of fault to see how my data looks like. So yeah, for if I plot for a single simulation run up to 500 sample, we see that for the fault number 0, that is the normal case, most of the data lie within the threshold, so which is a good thing. For fault number 1, for before 20, when fault was not introduced, it lies perfectly within the threshold, and after that, it passes the threshold so that we know there is a fault number 1 can be easily detected. Same for fault number 2 as well. It's easily detected. Fault number 3, not so much. Fault number 4, this is leading to misdetection because this part has no fault. Still, using PCA method, it says, okay, there is a fault there, but no. Same for fault number 5. Fault number 6 is pretty good. Just after the fault, it shows that, okay, there is a deviation. Fault number 7, okay, good. Yeah, like that, you can see for all different kind of fault scenarios. But in principal component analysis, we saw that there are a lot of misdetection. So here there is no fault, but still the principal component algorithm says, okay, there is a fault. So that we need to check. And then, but I want to convert this into a binary vector of 0 and 1 so that when there is no fault, it will say 0. When there is a fault, it will say 1. I just for that I created this function combined result where input will be my reconstruction loss and threshold will be the threshold I set for fault free condition. So the result will be if the value of the reconstruction loss is greater than threshold, then it will say result equal to 1, and then I'm converting that boolean value to a float. Finally, what I'm doing, I'm obtaining the F1 score and accuracy score for all the different type of faults except for fault 3 and fault 9. And why is that? For that, I I was looking through different papers and I saw that uh, look this part. Three scenarios, that is fault 3, fault 9 and fault 5 give poor fault detection rate for all the techniques and hence they have been excluded. it has been shown in this paper as well. That's why this the fault 3, fault 9, and fault 5 are not very they keep on getting false result. They're very similar to the healthy condition. That's why it's difficult to detect them. So that's why they have been excluded in many research paper. But for my evaluation, I did not exclude the fault 9. Sorry, I did not exclude the fault 5. I just exclude fault 3 and fault 9. So what I did is iterate through all fault condition from 0 to 21, just not 3 and 9. And for that, I obtained the F1 score and accuracy score. This is very similar to the previous video where I YPRED is my the prediction, the 0 1 matrix using the combined result for this one, and Y true is the ground truth. For when F norm is 0, that means all the cases are healthy condition, and when else all the conditions are 1, that is fault condition, except for first 21 values because the fault was introduced after 20th sample. Then I'm just importing some matrices and just obtaining the F1 score and accuracy. And yeah, you can see that this is pretty good because, but we can see there is a lot of misdetection rate. So this 21 are supposed to be the true label for them is 0, but the this model is predicting them to be 1. So yeah, it's called misdetection rate. This high, pretty high. So finally, what I did, the same thing that I did is basically the same function that I did in the previous one to get a single score for this entire method. What I did is I combined all the F1 score for 21 faults except for 3 and 9, and I averaged them out, which came out to be 0.53 for F1 score and 0.96 for the accuracy. So if you just use accuracy, you can be misinterpreted that your model is very good, but instead it's not. It's giving a lot of false alarm, which is not ideal in an industry case because you have to shut down your machine every time you see a false. Okay, so that was about it. I already updated that here. So the conclusion was that for now, the statistical method performed better than doing principal component analysis based reconstruction because when you use this, you lose interpretability as well. All the sensor data are combined to give you principal components so that you don't know which part has the highest error. But statistical method gives you pure idea because you know which sensor value has been deviated. Alright, so in the next part of the video, we'll see how you can use autoencoder neural network to do the same anomaly detection based on reconstruction. So see you on the next video.